Okay, we'll get started. In this section, we're going to be going through 3E and 3F. So that's going to be Newton's third law. So we'll get started with the first section. So Newton's third law, not to be confused with the second. So it describes how forces act on objects. Now, what does that mean? Well, this is how it's written usually formally, this quote right here. So whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. So what that's saying basically, right, you have two objects and they, one push, like if let's say A pushes on B, there's going to be a force from, B on A. It's just basically saying that, there's a result of, there's a reaction to forces. So the first force in this interaction up here is called the action force. Action. And then there's going to be a force that responds to that will be called the reaction force. So the action force, and then whatever responds to it, you're going to call that the reaction force. So with this, there's a couple things to keep in mind when the gist is pretty straightforward, but a couple things to keep in mind. The first about these forces is that these forces are going to be equivalent in magnitude, right? Remember that means size. So let's say, I'll give you another example. Let's say you push on a wall, right? Sure. You push on a wall with 5 newtons. That wall is going to push back on you with 5 newtons as well. So that's really what the third law is saying. Action, reaction, and it's important to keep in mind that these forces are going to be equal in size. So if you push with 5, you're going to get pushed back with 5. These forces are going to be opposite in direction. So in this example, right, you push the wall to the right, the wall is going to push you to the left. So they're going to be opposite. And the last thing is to keep in mind is they always act on different objects. So again, one of these forces is actually acting on the wall, is pushing the wall. The other force is pushing you. So that's important to keep in mind. So Newton's third law, what it's saying is fairly straightforward. There's a couple tricks to it. But again, for every action, there's an equal and opposite reaction. There's action force, reaction force. And keep in mind that those forces are equal, meaning they're the same size, right? Same size force. They're going to be in opposite directions, those two forces, and they're going to be actually on different things. So that's the basics of what the third law is saying. That idea of action and reaction. All right, so let's move on to the next page. And this page is really talking about some of the tricks. I don't know if I'd say tricks, but it's talking about some of the subtleties and some of the things that pop up out of the third law. So if you have two objects exerting forces on each other and they're isolated from all other objects, the force of each of them is going to be the same. But there's a condition here. So again, if you have two, and I'll give you an example down here, I'll draw it out. So if you have two objects, let's say you have, I don't know, small car, and let's say you had a larger car. So again, two objects, and there's no other forces, or there's no other forces besides, the force of them pushing on each other. Let's say they got in an accident. Those forces are going to be the same. So the force right here, force, applied 1, force applied 2, they're going to be the same size. But what's kind of tricky is the accelerations of the two objects may be different. So again, the third law says, okay, well, any type of interaction, the forces are going to be the same, the acceleration might be different. And there's a couple reasons you might see a different acceleration, or you might see the velocity change of these objects. Now these objects could have different masses, kind of like the example down here. So if you have a small car and it runs into this really big car, the forces on them are technically the same, but what's different is the mass. So there's going to be a different acceleration. And by the second law, if you have a big mass, so if your mass is large, your acceleration is going to be smaller. And again, if you have a small mass, like the other car right here, so if your mass is smaller, your acceleration is going to be larger. So again, the larger mass is going to have a smaller acceleration. So that kind of makes sense. Even though the force is the same, if you have a mass that's larger, your acceleration is going to be smaller, and kind of vice versa. And the other thing to kind of keep in mind is that the third law, right, it talks about an action and a reaction force, but there could be lots of other forces acting on it. So if you have a situation like many of the ones you've seen already, there might be several forces acting. It might not just be two things pushing on each other, right? In this situation, you could have, I don't know, you could have the force of air resistance, and you could have some friction in there, right? You could have a lot of forces, and when you add other forces to it, the net force is going to be different, and your acceleration is going to be different. So it's going to be hard to kind of tease out to figure out exactly, what the result of, just the action-reaction force are. It's going to be hard to figure out what happened. So that's important to keep in mind. So again, the section, to summarize, what it's saying is like, okay, third law is always valid. The action-reaction force are always the same. You push on the wall while pushes on you, the same amount. Two cars hit each other, they're going to have the same force. But the acceleration might be different. So again, the result of what that force has on those objects might be different. So again, it could be because they have different masses, or it could be because there are other forces acting on those objects. But again, they're going to have the same force, but the interaction might be different. Just like this, just to give you one more example, like if you, I don't know, had like a train, and I don't know, you put like a toy car in front of that train, technically there's the same force on both of those things. There's the same force on the toy car as there is on that train, technically, by the third law. But what's going to happen is one of those masses is huge and one of them is tiny. So, you're going to see different accelerations. You're going to see the toy car get like obliterated, and the train's really not going to notice much. So again, it's a little tricky because they have different accelerations even though they technically have the same force on them. So last thing, let's see a problem out with this. Problem. So see if you can solve this first before I go through it. Again, this one is a little conceptually tricky, not terrible. Make sure you solve it. Okay, so I'll go through this one. So we have a blue car, 1,200 kilograms, runs into a parked red truck, 5,000 kilograms, and there's a force of 1,000 that the red truck experiences. So it's saying, what's the force and acceleration of the blue car? Neglect friction. So I'm going to draw this out using my expert drawing abilities. We got car here, and I want to write the word blue, so it's blue. And then I'm going to draw a larger car here, our truck, and I'm going to label it red so it's red. So they're running into each other, and there's two forces really. There might be, well, there's really no other ones because there's no friction, and we really wouldn't take into account air resistance unless it says. So we have force applied on the blue car, and then we have the force applied on the red car, so I'm going to call it FAB and FAR. So those are the forces. It's saying like, okay, what's this force right here? What's the force? What's FAB? And then what's the acceleration right here? That's what it's asking. So the first one, let's think about the force. So by the third law, in this situation, right, this interaction, the forces are equal and opposite. FAB. So again, if you have a red truck experiences a force of 1,000 newtons, technically, the blue car, it's going to have the same magnitude, meaning it's going to have the same size. It's going to be 1,000, but it's going to be in the opposite direction. So they're going to have the same magnitude, but the blue car is just, it's going to be in the flip direction. So maybe I technically shouldn't write equal, I don't know. So it's just know that the force on the blue car is going to be the same size as the force on the red truck, but it's going to be negative. So it's going to be negative 1,000. So that's the first part. It's just that's just true by the third law. That's exactly what the third law says. And then the second one is saying, okay, what's the acceleration on the blue car? To do that, we're going to do out the net force in the x. There's really only one force to worry about because there's no friction. That would be the applied force on the blue. It's equal to mass times the acceleration. So FAB would be what? Negative 1,000. The mass is given as 1,200. Yes, that's right, 1,200 times A. And then we're going to divide out. So A is what? Negative 0.83 repeating meters per second squared. And that's A. So that's the idea. Again, it's just, you really just have to realize, okay, forces are equal. And then I can look at the second law and I can get the acceleration out. So that's really it for the third law. So again, make sure you have all of the notes, the blanks in the notes copied down. Make sure you have the solution for this problem copied down. I will repeat that again. Make sure you have the solution copied down for this problem. And that's it for now.